Hi everybody, I'm Alexis and today we're going to speak about stable deep learning algorithms for forward-backward stochastic differential equations. In simple words, that means we use neural networks to solve partial differential equations. First of all, I'm a PhD student in the computing department of Imperial College London. I'm supervised by Dr. Panos Parpas from the computational optimization group. And I also meet regularly with Dr. Nicholas Kentas and Professor Greg Pavliotis from the Department of Mathematics. I'm working on smoothing techniques and implicit gradient methods, and I'm also doing an internship within JP Morgan AI and machine learning. This work has been done with Batu Anguler and Dr. Panos Parpas, and we had the opportunity to present this project at NeurIPS 2019 in Vancouver, during the Robust AI in Financial Services workshop. The paper is available on arXiv here, and the poster is available on my personal website at this address. After a short introduction, I will explain the links between partial differential equations and stochastic differential equations. I will introduce you to this deep backward stochastic differential equation, which is basically these neural networks we build on top of SDEs. I will then move to stability and generalization issues we had and we tried to tackle using some techniques. And I will also present results we had on improvement on computational efficiency before concluding at the end of this presentation. So partial differential equations are everywhere. It can be in quantum mechanics, classical mechanics, but also financial mathematics with the famous Black-Scholes equation. The problem with those PDEs is there is usually no closed form solution. That means we have to use numerical techniques. But another problem with numerical techniques is they usually do not scale well with the dimension of the problem. And we name that the curse of dimensionality, which means basically the time to solve the problem grows exponentially with respect to the dimension of the problem. And we claim that the techniques that I will present later is less sensitive to that because we don't make any discretization in space. So first of all, a few definitions. A stochastic process can be defined by a stochastic differential equation with the variable of interest x of t. And it can be defined with two continuous functions, the drift here and the volatility here. And the last term is actually Brownian motion, which turns out to be the limit of a random walk when delta t is close to 0. On the right side of the slide, I have plotted two different paths. So the red one has actually a very small volatility, but he has a trend, the drift, which is equals to 1. As opposed to the black path, where the volatility is very high, but the drift is very small. And you can see, for example, on the black line, there is way more noise than the red one. And so you can play with those parameters to adjust a shape of the path. And so a few stochastic processes that are famous would be the geometric Brownian motion, which is often used in finance to model stocks. And both the Ornstein, Uhlenbeck, and Cox Ingersoll-Ross processes that are basically used to model interest rate. Okay, so we'll see the links between PDEs and SDEs. So let's say you start with this SDE, okay? And we know from the Fokker-Plant equation, the transition probabilities P is ruled by this equation. I don't want to go much into details, but you can see here a term, a derivative with respect to time, a derivative with respect to x, and a second derivative with respect to x, okay? And now, what if we apply this formula to the very example of d of x equals to dwt. In that case, you don't have any drift, so you can delete that term, and sigma basically equals to 1, okay? So you only left with the term that says derivative of p with respect to t equals to 1/2 of second derivative of p with respect to x. And this equation is the heat equation. And we know the solution of the heat equation is the Gaussian distribution. On the other side, you can have the reasoning by looking at the different paths that have been sampled from a Brownian motion. So you can see here, like you have like 100 different paths that have been sampled from a Brownian motion. And you can check after t equals to 1, what is the distribution of the value obtained. And you realize basically you end up with a Gaussian distribution. So everything is consistent here, and that should show the links that exist in between PDEs and SDEs. So the previous slide was for the linear case. In the nonlinear case and for parabolic PDEs of the following form, it's slightly more complicated because you not end up just with one single SDEs, but instead you end up with a system of forward and backward SDEs. The first one drives the evolution of x with an initial condition here, and the second one drives the evolution of y with a terminal condition here, okay? And you can see here, it's a drift function here, you got the volatility function here, and the function phi here is the one here, okay? And this system here is basically equivalent to the above PDE when we take y of t equals to u of t and x of t, and z of t to be the gradient of that, okay? And a simple way to think about it could be, in finance, you can see x of t to be the price of the underlying assets, and y of t to be the price of a derivative, right? And an easy example could be a call option, because for a call option, we know very well the terminal condition. If you have the strike here, the price here, and the payoff here on the y-axis, you just end up with a payoff which has this form, okay? So we know very well the terminal condition, but the main goal is to have the price before this terminal condition, right? For every t between now and the expiry date of the derivative, okay? Now we know there are strong links in between PDEs and SDEs. The idea is not to work on the PDE itself, but rather work on the SDE. And then using a neural network to map the function y equals to u of t and x, okay? And next step would be to compute z, which is the gradient of u. And it's gonna be easy for us because we can basically use the automatic differentiation from the deep learning libraries, like TensorFlow or PyTorch. And then the discretization is only in time, and is done by classic Euler scheme, where you can see here delta t in time and the delta w for the corresponding Brownian motion, which is just sampled from this normal distribution. As mentioned in the previous slides, the idea now is to use a neural network as a proxy for the function that maps t and x to y. So the function u that is parameterized by the weight of the neural network, function of t and x of t, okay? So here, as an input of the neural network, you have the vector x of t with d dimensions, and here you have the scalar t, right? And as an output, you just have the value of y of t. So here, this is a simple feed-forward neural network But you're going to see in a few slides that we also tried a different architecture. So this is a very important slide where you can see the whole process we applied. So remember discretization in time. Here you can see the n different time steps, okay? Starting from t equals t0, t equals t1, and t equals t big N, okay? And the previous slide was basically showing that step, a single time step, okay? So if you take this couple t0 x0, you take it as an input of the neural network, you will predict the value of y0. And then you compute that guy using the automatic differentiation. Having those two values, you can then compute x1. Remember, because we are not in the linear case, so x1 basically depends on those values. You use the neural network, and then as an output, you have y1, compute z1 by the automatic differentiation, and you do it for all the time steps up to the last one when you predict those values. An important thing here is basically the weights of the neural network are common to every time step. So the way we train the neural network is basically by minimizing the approximation error. And we build basically this big loss function, but it's actually not that complicated. So first of all, you have a sum here with respect to the number of time steps. And you have a sum here with respect to the number of trajectories, okay? And the value that is predicted by the neural network is that guy, okay? And we compare that value to what we claim that is kind of sort of true value here, which is the one obtained by applying the Euler scheme on the previous predicted value, okay? And then we have an extra term here that corresponds to the terminal condition we know for sure, okay? So here is the example of the Black-Scholes equation. So we basically try to solve the Black-Scholes equation with a very specific terminal condition, which is easy. And the reason why we have chosen that is because we know the closed form solution is that function, okay? So we are able to compare the performance of the neural network versus the closed form solution, okay? And on this graph, you can basically see two different paths, the exact one and the one that has been learned using the neural network. But the overall experiment was made on 100 different paths with 50 different time steps and a vector of x of 100 dimensions. And you can see on the right side here the evolution of the error through time. And the error is averaged through the 100 different trajectories, okay? So it seems to work very well, but in the next step, we will introduce a few concepts to improve that results. Okay, so for the next two slides, we'll see how we can see a neural network has a dynamical system. So remember, for now, we have only considered a feed-forward neural network, and we can basically see the feed-forward neural network as being defined by this relation, where you can see the next layer with respect to the previous one and a set of parameters theta, and f is a nonlinear transformation, okay? If we move to a different architecture, ResNet, on top of that, you had the concept of skip connection. And this is explained here in the original drawing from the paper. And you can see here the skip connection that takes the input x and it brings it here, okay? Without going through this weight layer and this second weight layer, okay? So the relation you have between layers is slightly different and you end up with this, okay? And this is for like specific time steps. But if you take like very small time steps and make them tend close to 0, you end up with this relation, which is basically an ODE. And from that ODE, some stability properties can be derived. So here you are a more sophisticated version of the ResNet we saw before. So this architecture is called ResNet, and if we use the term associative to dynamical systems, it's called a non-autonomous input-output stable neural network. So that means basically the output is input dependent, and this is because of U here, which is the input of the neural network, okay? And you have A, B, and C that are trainable parameters. What is interesting to note is we constrain the form of A so that we have a symmetric definite negative, a matrix. And the intuition behind this is if you solve the first order differential equation, you just end up with a solution like this. And you just don't want that to tend to plus infinity when t goes to infinity, okay? So that's why we constrain A to be that form, and epsilon is just an hyperparameter to make sure the eigenvalue are strictly negative, okay? And an exercise we can try is that by taking b equals to 0 and h equals to 1, you can basically find the original form of the ResNet equals x of t plus a function of f of t and theta t, where the parameters here are A and C. So here you can see the different results we had during our experiments on the Black-Scholes equation. So we have compared 3 different architectures, fully connected here in black. In gray, you have the ResNet, and in red, you have NiceNet, okay? So on the left side, the first graph, you can see the relative error with respect to the relative distance to the initial condition used for training. What is interesting with us is basically the neural network can't overfit on anything but the initial condition. So by making this experiment, we basically assess this generalization of our neural network, okay? And we can see here, basically, NiceNet is doing very well. On the right side of the slide, you can see here the loss function through the training, through the different iterations we made for training. And what you can see here is that you see massive jumps for the fully connected neural network, but you can't see those jumps for the ResNet nor for the NiceNet. So we tend to have like a way smoother loss function, which is a good sign for stability. And we can see here both ResNet and NiceNet are doing very well. So what we have tried too is multi-level techniques. So in our case, it can be seen as a warm-up procedure. So remember, we have this discretization scheme in time. And here we slightly change it so that we can basically adjust the time steps, okay? And we have like different levels, L, okay? And we basically define the time steps at level L by this relation. So what we do, basically, we start with very large time steps, H0, right? So we train the model until the loss does not decrease substantially, okay? Then we refine the time steps by using this relation. So let's say m equals to 2. So you're gonna have like h2 equal to h1 divided by 2 equals to h0 divided by 4, okay? Which is exactly h0 divided by 2 to the power 2, okay? Then you retrain the model until the loss does not decrease substantially. And then you basically repeat steps 2 and 3 until you get to the point you have the desired time step to solve your problem. So here are the different results of the experiment we conducted with these multi-level techniques. So we start with a very loose time step, which is level 1 here. So on that particular example, we have only 3 different points. Then you train a bit, you refine to level 2, you train a bit, refine to level 3, up to the point you reach the level of refinement you wanted for your solution, which is a black line, okay? And basically using these multi-level techniques is roughly 10 times faster than using the single level techniques, which is basically training your neural network on the super fine time steps and the final time steps. So, and whatever the architecture, this ratio remains roughly constant. So by adopting this technique, you can expect to have like convergence 10 times faster than using the single level. So during this project, we reviewed different proposals for the solution of high-dimensional PDEs using deep learning. We managed to have a better understanding on the stability, robustness, and generalization side. We tested different architecture, mainly ResNet and ResNet, and we show, for example, ResNet is doing very well. We also improved time computation by order of magnitude using multi-level technique. I believe future work could involve more advanced discretization techniques, probably improved sampling methods, and obviously this technique could be applied to many other terminal conditions, over differential equations, and maybe could be also applied to industrial problems as well. So these are the main references that have been used for the project. You can see a book from Emmanuel Gobet, a paper from Pierre-Henri Labordère, and a paper as well from Massia Aresi. Thank you very much for watching this video.